4. State machines. State machines are a method of modeling systems whose output depends on the entire history of their inputs, and not just on the most recent input. Compared to purely functional systems, in which the output is purely determined by the input, state machines have a performance that is determined by its history. State machines can be used to model a wide variety of systems, including user interfaces with typed input, mouse clicks, etc. Conversations in which, for example, the meaning of a word "it" depends on the history of things that have been said. The state of a spacecraft, including which valves are open and closed, the levels of fuel and oxygen, etc., and the sequential patterns in DNA and what they mean. State machine models can either be continuous time or discrete time. In continuous time models, we typically assume continuous spaces for the range of values of inputs and outputs, and use differential equations to describe the system's dynamics. This is an interesting and important approach, but it is hard to use it to describe the desired behavior of our robots, for example. The loop of reading sensors, computing, and generating an output is inherently discrete and too slow to be well modeled as a continuous time process. Also, our control policies are often highly nonlinear and discontinuous. So in this class, we will concentrate on discrete time models, meaning models whose inputs and outputs are determined at specific increments of time and which are synchronized to those specific time samples. Furthermore, in this chapter, we will make no assumptions about the form of the dependence of the output on the time history of inputs. It can be an arbitrary function. Generally speaking, we can think of the job of an embedded system as performing a transduction from a stream, infinite sequence of input values to a stream of output values. In order to specify the behavior of a system whose output depends on the history of its inputs mathematically, you could think of trying to specify a mapping from I1IT, sequences of previous inputs, to EOT, current output. But that could become very complicated to specify or execute as the history gets longer. In the state machine approach, we try to find some set of states of the system which capture the essential properties of the history of the inputs and are used to determine the current output of the system as well as its next state. It is an interesting and sometimes difficult modeling problem to find a good state machine model with the right set of states. In this chapter, we will explore how the ideas of PSAP can aid us in designing useful models. Chapter 4, State Machines, 6.01, Spring 2011, April 25, 2011, 118. One thing that is particularly interesting and important about state machine models is how many ways we can use them. In this class, we will use them in 3 fairly different ways. 1. Synthetically, state machines can specify a program for a robot or other system embedded in the world, with inputs being sensor readings and outputs being control commands. 2. Analytically, state machines can describe the behavior of the combination of a control system and the environment it is controlling. The input is generally a simple command to the entire system, and the output is some simple measure of the state of the system. The goal here is to analyze global properties of the coupled system, like whether it will converge to a steady state, or will oscillate, or will diverge. 3. Predictively, state machines can describe the way the environment works. For example, where I will end up if I drive down some road from some intersection. In this case, the inputs are control commands and the outputs are states of the external world. Such a model can be used to plan trajectories through the space of the external world to reach desirable states by considering different courses of action and using the model to predict their results. We will develop a single formalism and an encoding of that formalism in Python classes that will serve all 3 of these purposes. Our strategy for building very complex state machines will be, abstractly, the same strategy we use to build any kind of complex machine. We will define a set of primitive machines, in this case, an infinite class of primitive machines, and then a collection of combinators that allow us to put primitive machines together to make more complex machines, which can themselves be abstracted and combined to make more complex machines. 4.1 Primitive state machines. We can specify a transducer, a process that takes as input a sequence of values which serve as inputs to the state machine, and returns as output the set of outputs of the machine for each input, as a state machine, SM, by specifying a set of states, A set of inputs I also call the input vocabulary, a set of outputs. O also called the output vocabulary. A next state function in ITEST7, ST1 that maps the input at time t and the state at time t to the state at time t. One, an output function, OIT-OSTD7 OT, that maps the input at time t and the state at time t to the output at time t, and an initial state S0, which is the state at time 0. Here are a few state machines to give you an idea of the kind of systems we are considering. A tick-tock machine that generates the sequence 1, 0, 1, 0 is a finite state machine that IG ignores its input. The controller for a digital watch is a more complicated finite state machine. It transduces a sequence of inputs, combination of button presses, into a sequence of outputs, combinations of segments illuminated in the display. The controller for a bank of elevators in a large office building. It transduces the current set of buttons being pressed and sensors in the elevators for position, open doors, etc., into commands to the elevators to move up or down and open or close their doors. Chapter 4, State Machines 6.01, Spring 2011, April 25, 2011, 119. The very simplest kind of state machine is a pure function. If the machine has no state, and the output function is purely a function of the input, for example, OTIT1, then we have an immediate functional relationship between inputs and outputs on the same time step. Another simple class of SMS are finite state machines, for which the set of possible states is finite. The elevator controller can be thought of as a finite state machine if elevators are modeled as being only at one floor or another, or possibly between floors. But if the controller models the exact position of the elevator, for the purpose of stopping smoothly at each floor, for example, then it will be most easily expressed using real numbers for the state, though any real instantiation of it can ultimately only have finite precision. A different large class of SMS are describable as linear, time-invariant LTI systems. We will discuss these in detail Chapter 4, 1.1 examples. Let's look at several examples of state machines with complete formal definitions. 4.1.1.1 Language Acceptor. Here is a finite state machine whose output is true if the input string adheres to a simple pattern and false otherwise. In this case, the pattern has to be A, B, C, A, B, C, A, B, C. It uses the states 0, 1, and 2 to stand for the situations in which it is expecting an A, B, and C respectively. And it uses state 3 for the situation in which it has seen an input that was not the one that was expected. Once the machine goes to state 3, sometimes called a rejecting state, it never exits that state. 0, 1, 2, 3, I, A, B, C, O, true, false, 1 of S0, I, A, 2 of S1, I, B, and S, I, 0 of S2, I, C3, otherwise false of NS, I, 3 OS, I, true otherwise, S0, 0. Figure 4.1 shows a state transition diagram for this state machine. Each circle represents a state. The arcs connecting the circles represent possible transitions the machine can make. The arcs are labeled with a pair I, O, which means that if the machine is in the state denoted by a circle with label S and gets an input, then the arc points to the next state, NS, I, and the output generated OS, IO. Some arcs have several labels, indicating that there are many different inputs that will cause the same transition. Arcs can only be traversed in the direction of the arrow. For a state transition diagram to be complete, there must be an arrow emerging from each state for each possible input I. If the next state is the same for some inputs, then we draw the graph more compactly by using a single arrow with multiple labels, as you will see below. Chapter 4, State Machines 6.01, Spring 2011, April 25th, 2011, 120. 0, 3, 2, 1, C, true, a false B, false, B, false, C, false, a true B, true, a false C, false, a false B, false, C, false. Figure 4.1 State Transition Diagram for Language Acceptor. We will use tables like the following one to examine the evolution of a state machine. Time 0, 1, 2, D, input I0, I1, I2, state S0, S1, S2, output O1, O2, O3. For each column in the table, given the current input value and state, we can use the output function ER to determine the output in that column. And we use the N function applied to that input